Let's recap the most important information regarding combinatorics. In probability, combinatorics appears when we break up a problem into a series of simpler tasks. This is a very common procedure to follow. The starting point of the use of combinatorics in probability is the fundamental theorem of counting. A theorem says that if we have a job that can be performed in T1, T2, Tk separate tasks, and each one of them can be performed in n1, n2, nk ways, then the entire job can be performed in the product of n1, n2, nk ways. We have immediately used the fundamental theorem of counting in order to enumerate the number of ways in which we can choose R items among n1s. If we consider ordering but not replacement, then this number here is given by the fraction between n factorial and n minus r factorial. If we consider both ordering and replacement, then this number is given by n to the power r. If we don't consider neither ordering nor replacement, then this number is given by the combinations between n and r. The most difficult scenario to treat mathematically was the one in which we don't consider ordering, but we consider replacement. In this case, this number here has this expression. Be aware of the fact that this formula will appear very often in the following. It is possible to use the counting technique that we have learned in the previous lesson in the case in which the sample space S is finite and all the outcomes in S are equally likely to happen. In general, we call cardinality the number of elements of a set. So, if the sample space S is given by the outcomes Sn, Sn, then its cardinality will be n. Saying that all the outcomes are equally likely means that the probability associated to each singleton event, as I recall written like this, is identical. Moreover, since the probabilities must sum up to 1, we must necessarily have that the probability of each single singleton event is 1 over n. Moreover, every event can be written as the disjoint union of the outcomes that it contains, like this. Thus, using the second Kolmogorov axiom, we have that the probability of the event E is the probability of this disjoint union. The second Kolmogorov axiom says that we can transform this into the sum of the probability of each event, but since these probabilities are all equal to 1 over n, we can write this summation here. But since 1 over n is a constant, we can take it off the sum, like this. And we are left with the sum of 1 as many times as the number of outcomes in the event E. This is precisely the cardinality of E that we have to divide by n. So, to recap, if we have a random experiment such that its sample space is finite and all the outcomes are equally likely, then the probability of each event is given by the fraction between the cardinality of the event and the number of outcomes. Sometimes the cardinality of E can be computed directly. Some other times it requires the counting techniques that we have learned in the last lesson. We are now going to examine two examples. Of course, we start with the simplest one, but in the second, we will use the counting techniques that we have learned in the previous lesson. Consider the random experiment of rolling two identical dice. The sample space S will be given by all the unordered couples of numbers between 1 and 6, Hence, the cardinality of the sample space would be 36. We are interested in computing the probability that we get at least 1/6 with a single roll of the two dice. To compute this probability, we can proceed like this. We consider the event E given by the couples in which we are sure that 6 pops out from the first die, and the event F given by the couples in which we are sure that 6 pops out from the second die. Since we are interested in the probability of having at least 1/6, it doesn't matter if 6 pops out after rolling the first or the second die. Hence, the probability that we are searching for is given by the probability of the event E united with the event F. However, we have already seen that this probability is given by the probability of E plus the probability of F minus the probability of the intersection between E and F. To compute the probabilities of E and F, we must consider the fact that there are 6 ways in which both events may occur. In fact, M runs through a set of 6 integer numbers. Hence, the probability of E is equal to the probability of F, and thanks to this equation, it is equal to 6 divided by 36, that is 1 divided by 6. So we have computed this probability and this probability. Now we have to compute this probability here. In order to do that, we observe that the intersection between E and F is just the couple 6, 6. Since we have just an element in this set, we have that its cardinality is 1, and so again, thanks to this equation, we have that the probability of the intersection between the two events is just 1 over 36. Now we have all the information that we need. The probability of having at least 1/6 in the rolling of two identical dice is 1 divided by 6 plus the same minus 1 divided by 36, which is 11 divided by 36. Which gives roughly 30% chance. Notice that there is absolutely nothing special about the number 6, and so this probability is exactly the same if we replace 6 with any other number between 1 and 5. So the take-home message that you can use to impress your friends is that when you throw two dice, you have almost 1 chance over 3 to obtain at least one fixed number of your choice. Let's now pass to a more complicated example, that is the game of poker. As you may know, the standard poker deck has 52 cards, which are depicted here. Clubs, diamonds, hearts, and spades are called the kind of the cards. Whenever you fix a kind, for example diamond, you have 13 denominations, from the ace to the king. Finally, we call hand 5 cards obtained from a well-shuffled deck. Regarding counting, we can say that in poker, cards are always sampled without replacement from the deck. In this example, we choose to look at the hand all at once. That is, we don't mind when the 5 cards have been given to us. Thus, the probability counting in this example is unordered and without replacement. The corresponding place in the previous table will be this one here at the intersection, with n given by 52, the number of cards, and r given by 5, the number of cards in one hand. So the cardinality of the sample space, given by all possible hands obtained from the deck, unordered and without replacement, is given by this binomial coefficient or this explicit number. Using formula 1,6, we can assign to the event E that consists in having one hand of 5 specific cards the following probability. The probability of E is one hand divided by all the possible hands, that is roughly 4 times 10 to the power minus 7. Thus, without any surprise, the probability of guessing exactly the 5 cards in one hand is very, very small. Now let's compute the probability of another event, that is, having a poker of 4 aces in our hand. To find this probability, we must count how many different hands there are with 4 aces. For that, notice that if we specify that 4 of the cards that we have in our hand are aces, then there are 52 minus 4, that is 48, different ways of specifying the fifth card. And this implies that there are exactly 48 hands with 4 aces in them. Applying formula 1,6, we get that the probability of having a poker of 4 aces in one hand is given by 48 divided by the cardinality of the sample space, that is around 2 times 10 to the power minus 5. Here the take-home message is, if you are playing poker with a bunch of friends and one of them claims to have received a hand with a poker of 4 aces, either your friend is very lucky, or much more probably, your friend is cheating. Now we want to compute the probability of another event, that is, having 4 cards of the same kind in one hand. The job of counting here can be decomposed in 2 different tasks. The first corresponds to sampling the cards of the same kind from the desk, but we know that this can be accomplished in 13 different ways. The second task consists in sampling the fifth card from the remaining cards of the deck, and this can be performed in 52 minus 4, that is 48 different ways. Notice that this is the correct counting, because we have demanded to have at least 4 cards of the same kind, and we didn't exclude the possibility of having 5 of them. So all the remaining cards of the deck must be counted, and not only those having another kind with respect to the previous 4. Since we have decomposed the job of counting in 2 different tasks, we have to apply the fundamental theorem of counting, which says that the total number of hands with at least 4 cards of the same kind is 13 times 48. The result is 624, so the probability of having at least 4 cards of the same kind in one hand is 624 divided by the cardinality of the sample space, which gives this number here, which is around 0.024%, slightly less than 1 chance over 4,000. The final event that we consider is having exactly one pair of 2 kinds in one hand. That is, for example, a 7 of spades and a 7 of hearts, but not 2 pairs, not 3 of a different kind, etc., etc. This is a very interesting example because it will force us to use different counting techniques. First of all, in order to define the pair, we must specify a denomination, that is ace, 2, 3, etc., etc. And we know that there are exactly 13 denominations. Then we must specify 2 kinds of cards among the 4 that exist. If you think about it for a second, you see that this specification is unordered and without replacement. So if you take a look at the table of counting, you see that the number of choices that we can make in this case is given by this binomial coefficient, which gives 6. Then we also have to take into account that the other three cards must have a different denomination with respect to the one that we have chosen for our pair. Otherwise, we will have three of a kind or more. And we have explicitly said that we want to avoid this possibility, right? Again, think about it for a second. No ordering or replacement is involved in the choice of the remaining 12 denominations for the three cards that remain to compose our hand. So the number of choices is given again by a binomial coefficient, but in this case we have to put 12 here and 3 here, which gives 220. Finally, the three remaining cards have a kind, and this can be selected among the four possible ones. And this can be done in 4 cubed, that is 64 ways. To conclude, if we take into account all these items, we have that the probability of having exactly one pair is given by 13 times 6 times 220 times 64, there it is, divided by the number of samples, which gives roughly 42%. This example was quite long, and so it's a nice idea to recap what we have done. The sample space that we have considered consists in all the hands of 5 cards that we can get from a well-shuffled deck of poker. These hands come in a finite number n and they are equally likely. So, given an event E associated with the game of poker, we can use equation 1/6 to write the probability of the event as the cardinality associated to the event divided by n. In the example, we have considered 4 types of events. Finally, by using the counting methods that we have learned in the last lesson, we have computed the cardinality of each event, which in turn gave us the possibility to compute the probability of each event. You don't have to worry if at the beginning the application of the counting methods may seem complicated, because as always it becomes easier and easier as we put it in practice. In this section, we're going to define and analyze the very important concept of conditional probability. All the probabilities that we have considered so far were unconditional, in the sense that they were calculated with respect to a fixed sample space S. However, we're going to see that in many situations, we are able to update the sample space based on another information that we have acquired. In such cases, the probabilities that we compute are called conditional. As always, instead of giving you directly the abstract definition of conditional probability, I prefer to introduce it through a motivational example. Let's consider this situation. 4 cards are dealt from the top of a well-shuffled deck. What we want to know is what's the probability that these 4 cards are the 4 queens of the deck. We're going to answer this question using 2 methods. In the first method, we use the counting techniques that we have learned in the previous section. We ask ourselves, what's the number of distinct group of 4 cards, unordered and without replacement, that we can gather from the deck? Using the counting techniques, we know that we have to use a binomial coefficient, where here we have to insert the number of cards, that is 52, and here we have to introduce the number of cards belonging to our group, that is 4. Among these groups of 4 cards, there is only one group that consists of the 4 queens. Moreover, every group is equally likely, and we are dealing with a finite number of them. Hence, we can use equation 1/6 to compute the probability of being given all the 4 queens, which is 1 over this binomial coefficient. Now let's use the second method, which is based on an updating argument. Let's see what it means. We start by observing that there are 4 queens in the deck, So the probability that the first card is a queen is 4 divided by 52. Now, given that the first card is a queen, which means under the hypothesis that the first card is a queen, there remain 3 queens in 51 cards. So the probability that the second card is a queen is 3 over 51. If we iterate this argument until we arrive to 4 cards, and we use the fundamental theorem of counting, we have that the desired probability is this one here. If you perform the explicit computation, you find exactly 1 over this binomial coefficient. The second method shows that the act of taking out a queen from the deck conditions the number of remaining queens, and so the sample space must be updated. There are 2 take-home messages that we can gather from this example. If an event occurred, then its conditional probability must be 1. Why that? Well, because if we are under the hypothesis that an event occurred, what's its probability of occurrence? Of course, is 100%, that is 1. Moreover, all further occurrences must be calibrated with respect to the novel sample space and not with respect to the original one. Why that? Well, because in the example that we have just analyzed, after receiving the first queen, we have updated the probability of receiving another to 3 over 51, etc., etc. These are all examples of calibration of the sample space after the acquisition of a novel information. In particular, notice that if an event is incompatible with the novel sample space, that is, it cannot occur simultaneously with the events that have already occurred, then its conditional probability must be 0. For example, the event receiving a queen has probability 4 over 52 in the original sample space, but it has probability 0 in the sample space that has been updated after receiving 4 queens. In other words, receiving a queen is not compatible with having already received 4 queens. In other words, the event E of receiving a queen cannot occur simultaneously with the event of having already received 4 queens. This is why the conditional probability of E must be 0. In the next page, we're going to see that the mathematical definition of conditional probability takes into account these 2 essential features. Consider 2 events E and F in a sample space S, with the probability of F strictly greater than 0. Then the conditional probability of the event E given F, that is under the hypothesis that F occurs, it is written with this symbol here, and it's defined with this formula. The formula says that the conditional probability of E given F is given by the fraction between the probability of E intersected with F and the probability of F. Of course, we require that the probability of F is strictly greater than 0 to avoid a 0 denominator. Let's verify that this definition is coherent with what we expect. First of all, we must verify that the conditional probability of F given F is 1. That is, the probability of occurrence of F under the hypothesis that F occurs is 100%. If we introduce F instead of E in the definition, we have the probability of F intersected with F, which is of course F itself, divided by P of F, which is of course 1. Moreover, if E and F are incompatible, that is, their intersection is the empty set, then the probability of E intersected with F is equal to the probability of the empty set, which is 0. This implies that the conditional probability of E given F in this case is 0. Let's immediately use this mathematical definition to analyze a follow-up of the previous motivational example which will show one of the most important facts about conditional probability. It can be highly counterintuitive. In the previous motivational example, we have seen that the probability of getting all 4 queens is small, this number here. Now, alongside with the event described in the last example, that is the event E having 4 queens in 4 cards, we also consider these 3 other events, Fk, that is k queens in k cards, with k that goes from 1 to 3. We have to remark that if the event E occurs, then the first card is a queen, and so we have 1 queen in 1 card. The second card too, that is 2 queens in 2 cards, and also the third card, and so we have 3 queens in 3 cards. That is to say, if the event E occurs, then also all the events Fk occur. This means that the event E is a subset of all the events Fk, and so the intersection between E and Fk is equal to E for all k. Keeping this in mind, we have that the conditional probability of having 4 queens in 4 cards, given that we have k queens in k cards, that is the conditional probability of the event E given the event Fk, is the fraction between the probability of E and the probability of the events Fk, because E is equal to E intersected with Fk. The numerator is known from the previous example, and it is this number here. Now we have to compute the probability of the events Fk. We have that the number of distinct queens in a group of k cards without replacement and without considering the ordering is exactly this binomial coefficient here. Moreover, the number of possible different sets of k cards in the deck without replacement and without considering the ordering is this binomial coefficient here. As a consequence, the probability of the events Fk is the fraction between the previous binomial coefficients. So we get the conditional probability of the event E given the events Fk is given by this seemingly difficult fraction of binomial coefficients. However, if you write down the explicit expression of the binomial coefficients, you find this formula written with respect to the factorials. And then you see that you can simplify plenty of things. For example, 52 factorial, 4 factorial, and k factorial. Moreover, you see that 52 minus 4 is 48 factorial. So the final expression that you have is this one, that you can check being equal to 1 over this binomial coefficient. Now, if you let k run over 1, 2, and 3, you can get explicitly the 3 conditional probabilities. Before discussing the meaning of this result, let me show you how to compute, for example, this probability here. Using this formula with factorials, we have that the conditional probability of the event E given the event F3 is given by 48 factorial times 4 minus 3 factorial, which is 1 factorial that is 1, and so we avoid it. And then at the denominator we have 52 minus 3 factorial, which is 49 factorial. Then we use the fact that we can write 49 factorial as 49 times 48 factorial, and so we can eliminate this factor, and we remain with the fraction 1 over 49, that is around 0.02. Now let's get back to the interpretation of these 3 results. As you see, we have this strange behavior in which the probability of being given a queen increases given that we already had a queen in the previous occasion. In the following, we are going to deal with many situations in which conditional probabilities challenge our common sense. The take-home message here is that when we consider conditional probabilities, we must leave our common sense aside and use mathematics. At the beginning, it's very difficult, unnatural, to leave our common sense aside. For this reason, I prepared another example to try to convince you that this is the right thing to do. The following is a very famous problem presented by Martin Gardner in the Mathematical Games column of the Scientific American in 1959. It's called the Three Prisoners problem, and let's read it together. Three prisoners, A, B, and C, have worked hard to show that they are ready to be restored into the society. The warden of the prison receives a phone call from the state governor, who tells him that he chose at random the prisoner that will be set free among A, B, and C. He reveals his choice, but forbids the warden to reveal it to the prisoners before he arrives to the prison in person. The next day, prisoner A tries to get the warden to tell him who had been pardoned, but of course the warden says that he cannot reveal it. Prisoner A is particularly stubborn. In fact, the day after, he asks the warden to tell him at least the identity of one of the two prisoners who are going to remain in jail. In fact, he's a little bit more Machiavellic than that. In fact, he tells the warden, "If B is to be pardoned, give me C's name. If C is to be pardoned, give me B's name. And if I'm the one to be pardoned, then flip a coin to decide whether to give me the name B or C." Notice that the Machiavellic reasoning of prisoner A is correct, because the warden was told not to reveal the name of the person that was going to be pardoned. So, if he tells the name of a prisoner who's going to remain in jail, he doesn't break his promise to the governor. The warden, who knows probability, decides to tell A that B will remain in prison. Prisoner A didn't have the privilege to study probability and uses just his common sense to think that his chances to get out of prison have increased from 1/3 to 1/2, because now the choice is between him and the prisoner C. As you may have guessed, prisoner A is not only stubborn and Machiavellic, but he's also a big mouth, and he decides to secretly tell C that B will remain in prison. However, prisoner C, who knows probability, is very happy to hear that, because now he knows that his probability of being pardoned has increased from 1/3 to 2/3. Let's analyze the three prisoners problem from the perspective of conditional probability. First of all, we denote with A, B, and C, respectively, the event that prisoner A, prisoner B, or prisoner C is pardoned. Remember now that the governor chose at random who to pardon. So, before the warden says anything, we have identical probabilities. That is, P of A, B, and C are exactly the same, and their value is 1/3. Now we denote with W the event that the warden tells A that B will remain in prison. As we know, this event indeed occurs, so the previous probabilities must be updated to conditional ones. Since B remains in prison, the conditional probabilities of interest for us are the probability P of A given W and P of C given W. So now what remains to be done is to compute these probabilities here. Let's start with the probability P of W. This is the probability that the warden tells A that B remains in prison, but this probability is 1/2, because the warden will always name either B or C. Instead, this is the probability that A is pardoned and the warden tells him that B remains in prison. This is the key point of the reasoning. In fact, recall that if A is pardoned, then the warden agreed to flip a coin and decide to tell him that either B or C will remain in prison. But crucially, the act of flipping a coin is associated to a probability 1/2. So the probability of occurrence of these two events simultaneously is given by the probability of A times 1/2, that is 1 divided by 6. Finally, let's discuss the probability that C is pardoned and the warden tells A that B remains in prison. In this case, the behavior of the warden is deterministic and not probabilistic. In fact, recall that if C is pardoned, the warden agreed to tell A that B will remain in prison. So in this case, the warden is simply following a rule, and there is nothing probabilistic in that action. For this reason, the probability of this simultaneous event is equal to the probability of C, that was 1/3. The probability that A is pardoned, given that the warden tells him that B will remain in prison, is still 1/3. This is precisely the reason why the warden, who knows probability, agreed to the request of prisoner A. In fact, he knew that A was not going to obtain any novel information about his chance of getting out of prison. Instead, the conditional probability of C being pardoned, given that the warden tells A that B will remain in prison, has increased from 1/3 to 2/3. The take-home message is that conditional probabilities can be quite slippery, and they require a careful interpretation. In particular, don't trust your intuition when you're dealing with conditional probabilities. In the next lesson, we're going to introduce the very famous Bayes theorem that will allow us dealing with conditional probabilities in a much easier way.